Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh dan good afternoon to all of you. Right, so let's continue our chapter. So today we try to finish on the chapter 5. So this is the last chapter for our subject is for digital electronics. Right, so let's share the screen. Alright, so let's look first. Right, so that I mentioned to you. So this is last chapter, okay, chapter 5. Actually, before this, the last year. So this chapter will be no, because of our final exam until chapter 4. But for this semester, okay, so we have okay, we have one question on the chapter 5. So so we have to cover chapter 5. Chapter 5. Actually, chapter 5 is a topical lah, related to integrated circuit technology lah. Alright, so let's go for the chapter 5. Is the actually this is the last chapter, the last chapter for our subject. Okay, chapter 5 is the integrated circuit technology. Okay, so inside the integrated circuit technology, we have the TTL. Okay, TTL stands for Transistor-Transistor Logic, and CMOS. Okay, CMOS stands for complementary metal-oxide semiconductor. So, what is the inside an IC? So, what inside the integrated circuit lah? So, you can see this one. So, this is our IC that I think maybe some of you already see this IC. So actually on the IC we have a lot of type. So we have the small outlet of IC. Okay, we have the I will explain after this. The type of the IC. Okay, so inside this one, inside this IC we have the module. Sometimes we have so this is an example of the module inside the IC lah. So maybe we have the comparator, we have the adder, we have the marks or demarks. Okay, it means demark is the multiplier or demultiplier. Okay, we have the decoder, we have the encoder, flip-flop, latch, and so on. Okay, so this we call the module lah inside the IC. Actually, it's come from the conventional logic circuit lah. So for example, the comparator. So inside the comparator, or we have the adder. So inside the adder, we have the combination logic circuit to perform the operation of the module. So for example, the adder, right? So on the also in the IC we have the TTL. Okay, TTL that we call the transistor logic inverter. So you can see this one. So that's why we have the voltage supply here, and then this is ground. And also we have the CMOS. Okay, CMOS inverter. Either we have the CMOS inverter or we have the transistor logic inverter, as you can see inside the IC. Alright. Okay, so next we go for the logic family. Okay, so that mentioned to you before this, we have two types. Okay, first we have the CMOS, or step one we have the TTL that I mentioned in the first slide. Right. So actually we have another one. Okay, we have three families in the digital logic circuit. There is the CMOS. CMOS stands for complementary metal-oxide semiconductor. Okay, we have the bipolar IC that we call the transistor logic, and then another one is the by CMOS. By CMOS is the bipolar CMOS. Okay. Right. So actually, they differ in the type of the circuit component used internally to implement the logic function and operational parameters. Okay, and equal in the basic logic operation. For example, like CMOS and gate has the same logic operations as the bipolar. For example, bipolar and gate, and or by CMOS and gate. Okay, that means, for example, is we use the bipolar, that means the transistor is for the AND gate, something like this. It's the same operation. Okay. So we have AB. Okay. For the input, we have also the output with AB. Similar like by CMOS AND gate. For example, we have AB. So the output will be AB. Alright. So that's why some of the is the basic logic is equal lah. Okay, the basic logic is equal for the CMOS and the bipolar. Sorry, the CMOS and the CMOS and the TTL lah, the bipolar. Yeah. All right, so let's go for the CMOS. CMOS stand for complementary metal oxide semiconductor. Okay, so implemented with the combination of the P-type and N-type metal oxide semiconductor field effects transistor. Sometimes we call them MOSFET. Yeah, all right. So this is okay, the combination of the P-type and N-type are similar like transistor. So for example, the transistor we have two types. So we have the NPN and PNP lah. For example, like for our transistor, we have the PNP. Another one is a PNP. Okay, NPN and PNP lah. Right, so this is similar like CMOS. CMOS we have two types. So we have P types and N types metal oxide semiconductor that we call the MOSFET to implement the logic gate. As you can see in this circuit. So this is some example of the MOSFET. And then we have the inverter gate constructed from the CMOS. Okay. So the dominant among the logic families as bipolar logic appear to be the decline. All right, so we have the rules in handling the CMOS device. Okay, so first we have to put coupling capacitor across the power supply to each IC. Why? So why? Because of the so the CMOS device draw the spike. So the spike, so the current, okay, the current from the power supply, they have the spark. So when they are changed state at the clock transition, for example, this is we have the okay. So the clock transition, that means from the positive going pulse to negative going pulse. Okay, from the supply they have the sparks. Okay, so that's why we have to put some capacitor. Okay, so the capacitor we have to be coupling with capacitor across the power supply to protect our device because of the CMOS device draw the spike. Okay, the spike of the current very dangerous. Okay, to protect our CMOS. And then they put the capacitor the capacitor. So this capacitor act as a high pass filter so to filter the spike. Okay. Then for second rule is the never leave input floating Okay, why? Because they do not float high as the TTL. Okay, so unconnected input can cause the circuit to be oscillate widely so be oscillated widely. That's why the rule of handling the CMOS we have two rules. First, we have to put the decoupling capacitor because CMOS will be draw the spark of the current from the power supply, and second one will be never leave input floating. Okay. Then next we go for the TTL, the transistor logic. Sometimes we call the bipolar. Alright, bipolar. So use bipolar junction transistor BJT. I think maybe you are familiar. Before this, maybe you are familiar about the BJT. We call the BJT, okay, bipolar junction transistor. And then we have mentioned to you before this. We have two types. We have the PNP and another one we have NPN. So the bipolar need 5 volt 5 volt power supply Okay, this one is the 5 volt power supply. Okay, so this is some example. You can see in the figure is the example of inverter gate constructed with the TTL. Okay, so this is our transistor and this is transistor right? So this is the NPN and this one also NPN for them. Okay, so what does the number on IC? So as mentioned before this, maybe you can see the I said about the IC. So for example, the 4074 HC 112, 112. What is does mean? Okay, so for example, like 74 is still that is the logic IC lah, logic IC. Sometimes we can see the 54 is stripped, okay, which means that the device should operate over the wide range of the temperature lah. So there is a standard range, okay, for the domestic, commercials, industrials, military application. So every application they have the standard range. Okay, that's why we have to refer to, okay, we have to refer to data sheet. So for this IC, so what is the standard range for this IC? Because of the application, they have the standard range. Okay, for example, like demonstrates, okay, commercialized, industrial, and also on the military application, they have some standard range. And then for H, okay, so HC is the family of the device, which means the technology that has been used to construct the transistor within the circuit. So the HC means the high performance CMOS lah. Okay, high performance CMOS. And then 112 is the give the function of the device. For example, the gate, okay, flip-flops, counter. Okay, that is function lah. So for example, 112 maybe is the flip-flop or is the counter or is the gates. Okay, so this means here this is will be okay, will be tell about the IC, and then this one is the performance, okay, high performance, and this one is the function function of the IC. Okay, we have another example. So this is common meaning of the IC. Maybe you can see the capital for A, okay, the A, F, H, okay, C, and L. Okay, so this is common meaning to some of the letter in this logic family, the acronym. So for example, like A is for stand for advanced. Okay, F means fast. Okay, H means high speeds. Okay, high technology, for example. Okay, and then S means Scotty. Okay, Scotty technology, and C means CMOS, and L means low power or low voltage lah. So this is common meaning of the IC. All right. So next we go for the characteristic of the digital IC. All right. So we get here. This is some characteristics. So we have 6 characteristics. Okay. On the digital IC, used to compare their performance. Right. So normally you can refer on the data sheet. So there will be explained on the okay, on the power supply requirements. Okay, noise limit. So we have to know the noise range. Okay, the noise range for every IC that you want to use. Okay, for example, okay, this IC, all right, so they have the noise, certain noise, okay, the range of noise. So is it okay or not? Depends on, and then the speed of operations, okay, the power distribution, and then figure of merit and find out. So this is the some characteristic of the digital IC. Yeah. So normally the characteristic of the digital IC you can find on the data sheet of the every IC. Okay. Right, so maybe we go one by one. So that's mean on the mention to you is the chapter 5 is actually is more on the theoretical about the IC lah. Okay, so this is the characteristic of the IC. We have 6. Okay, we go one by one. First, we go for DC DC supply voltage. All right, so the supply voltage and the amount of power required by an IC is important characteristic required to choose the proper power supply lah. Okay, so normally mentioned here, okay, the nominal value of the DC power voltage for TTL is the 5 watts. Okay, so that mentioned before this, maybe to on the IC. Okay, so we have to give the supply. So for example, we have the IC. Okay, our IC. Okay, so for example, this indicator. All right, so 1, 2, 3, 4, 5 until 8, and then okay, so we have one pin for on this. For example, okay, we assume the one is the VCC and the for 9 for the ground up, for example. So you have to connect this IC to the VCC, okay, to the power supply to on this IC. If not, so this IC is not functional. Okay, so normally for TTL is the 5 volt, okay, 5 volts DC. And then the CMOS device are available in the different supply voltage category. So some, okay, for the CMOS, sometimes we have the, okay, you can find on 5 volts, okay, sometimes you can find on the 3.3. That means if you use the 3.3 IC, that means our IC we use the CMOS, okay. For the TTL normally will be fixed to 5 volts, okay. That's different. For the CMOS, they have the range of the supply. Okay, we have range of supply. Some, for example, like we have the 5 volt, 3.3. Okay, we have 3.3 volt, 2.5 volts, and 1.2 volts. All right, so that is the difference between the TTL and CMOS. All right, so for DC power voltage, okay, there is 4 different logic level specifications. Okay, so first we have the high level input voltage. So this range of input voltage is recognized by the gate as logic 1, all right? And then we have low level input voltage. Okay, so this range input voltage which is recognized by gate as the logic 0, all right? And then we have high level output voltage. Okay, actually this is for input, and then number 2 we have for output. So either we have the logic 0 or logic 1 lah. Okay, that means if the this one high level, okay, high level input voltage, that means the input is 1. Okay, if the low level input voltage we have 0. Similar like for the output, output, high level output, so we have 1. Okay, output 1, and then we have low level output voltage, we have the 0 lah. Okay, there is 4 difference. Okay, we have 4 different logic specification. Okay, so when we right, so on the, for example, like the CMOS, okay, the CMOS we have mentioned to you, we have range of the DC supply. We have 5 volt, for example, 3.3 volt, we have 2.5 volts, and some, okay, we have different okay, for example here, and for the TTL we have fixed for 5 volts. Okay, here is a CMOS 5 volts. All right, so you can see here the figure here actually is the 5 volt. All right, so they have range. Okay, they have range for logic 1. Okay, so for example like this one, 3.5 to 5 actually is the logic 1. All right, if 0 to 1.5, there is the logic 0, and then this is not allowed and allowed, okay, for this range. That's why for the DC power supply, all right, so they have the range for input, okay, for the high volt, high input or low input lah, for example. So for example, this one is the for the input. Okay, there's the range, okay, from 3.5 to 5 volt is the logic 1, then 0 to 1.5 is the logic 0. All right, so actually this is for the input. All right, as you can see, for the output, all right, for the output they have the small difference. Okay, so from 4.4 to here, so we can declare as the logic 1, and then from 0 to 0.33 is we can declare as the logic 0. Okay, we reduce the range, okay, for the output and input. Okay, this is the, for example, this is the 5 volt CMOS, right? So you can see here, so for the input we have the we give a range, bigger range compared than the output. All right, okay, and then okay, before this is the on the 5 volt CMOS. Now you can see on the 5 volt TTL, TTL transistor logic. As you can see, the difference between the input and output as before this. For the CMOS is quite different. Okay, for the CMOS from 4.5, for example. Okay, but for the TTL is for the logic 1, all right, from 2 to 5 volt. All right, 2 to 5 volt we can declare logic 1, and from the logic 0 is from 0 to 8.5 0.8. All right, so this is logic 0, and then this is not loud. Okay, and then for output, okay, so that's different lah. Okay, for this, for the CMOS, we have the small range, okay, small range of the of the output. But for the TTL, so we have biggest biggest range for the output, one lah. Okay, for the logic one, from 2.4 volt to 5 volt, and then for the low, okay, for the zero, from 0 to 0.4 volts. That is for okay, DC power supply for the inputs and outputs. Okay, next characteristic, we go for the noise immunity lah. So that mentioned to you, so noise, maybe you are study on the measurement and instrument. So every measurement or every instrument, there it will be introduced some noise. Okay, so that's why we call the noise is, we call the unwanted, okay, unwanted voltage or unwanted signal lah. Sometimes we call it unwanted signal or unwanted voltage here. So this one we can declare as the voltage now, right? That induced in the electrical circuits and can present the threat of to the proper operation of the circuits. Okay, so that is the noise. So the noise resource, okay, resources, okay, other conductor within the system pick up the high frequency electromagnetic radiation from the adjacent conductor, right? And then in order to be successfully affected by the noise, so the logic circuit must have a certain amounts of noise immunity. So we have to set the range, okay, for the noise. So this noise we can accept. So it's quite difficult to us to reduce to eliminate the noise, but we can set the range. Okay, so this noise we can accept. All right, that we call the noise immunity lah. Okay, this means we can put some range for the noise. Okay, so for example, this noise, okay, from we have, for example, for the output we have 5 volt. Okay, 5 volt for the output. So maybe the noise range from 4.5 to 5.5, that we can accept lah. Okay, that we call the noise immunity. This is the ability to tolerate a certain amount of unwanted voltage fluctuation. Okay, for example, like, okay, so if, for example, if we have a DC, okay, so this is our DC power supply. For example, we have 5 volts here. So the ideal is this is the ideal. The ideal case will be straight line, is the 5 volt. But if you zoom, okay, but for the real, so it's not like this. Actually, it's something like this. We have some noise here. Okay, called noise here. So if you, for example, like our signal, our clock, okay, that I mentioned to you. So if you see on the okay, on the oscilloscope, okay, when we put like this, so it's a very nice, okay, very nice shape here for the clock. All right, okay, but when we zoom, okay, actually when we zoom here, okay, you can zoom. For example, if you use the software MATLAB, so we can zoom here. All right, so when we zoom, so actually our signal will be like this. We have some okay, we have some overshoot here. Maybe we have not straight line, so we have some delay here, and then undershoot here, then go here, something like this. Something, it's not so nice. This is we call the ideal the ideal clock. Okay, for example, like this one is the ideal DC DC supply for example 5 volt. Okay, yes. So if you put as the ideal, so it will be like this, it will be straight line. But if you see the real time, actually we have there some noise so something like this. But this one we can declare as the, from this range to this range, we can declare as the noise or noise range, so that we can tolerate. Okay, we can tolerate a certain amount of unwanted voltage fluctuation to its input without changing the output state, right? So this is a okay example of the noise immunity. So for example, if noise voltage causes the input of the 5 volt CMOS drop below 3.5 volt in the high state, so the input is the unacceptable region lah. So like this, for example, if let's drop until 3.5 volt, so you can we can declare as the unacceptable region. Thus, the gate may be interpreted as the fluctuation below than 3.5 as low level lah. Okay, will be set as the low level. Alright, so if the noise cause the input to go above 1.5 volt in the low state with a certain condition is corrected. Okay, as you can see here. So this is for example, this is okay, the range that I mentioned to you. So this one is we can declare as the unallowed region. So this one we can okay. So if we have excessive noise cause the input to go the okay, the minimum. All right, so the gate may think that there is the low. Okay, this one for example is a low, this is a 0. Okay, so the input respond accordingly lah. All right, and then similar like for the lower lah. For the lower, if you have high, okay, we have the high noise here, so maybe we can okay, this is in the unallowed region. All right, so maybe the gate thing there is the height. Okay, this is for 1. Okay, for example, okay, so that's why we have the noise. You can noise margin. Okay, the margin. Okay, that you can set as the range noise range. So noise margin is a measure of circuit noise unity that's called the noise margin. So which is expressed in the volt. Okay, for example, for the high level noise margin and low level noise margin, so we have the here lah. Right, so you can see okay, for example here for the high, okay, high level noise margin, and this is a lower level noise margin. Okay, for example, for high level noise margin we set from 3.5 to 4.4. Okay, for example, the noise will be fluctuated for this range for example, for this range, for example, like this. Okay, and then this one, okay, for low noise, okay, margin maybe from 0.33 to 1.5 volt. Okay. This one we can set as we can call as the noise margin. Okay, so this is an example for the noise margin. We have high level noise margin and lower level noise margin. You can see here. Okay, for example, so this is for high, and then right. So this is for output. Okay, output high. We have 4.4. Right. So this cannot be dropped until 3.5 lah. Okay, 3.5. If 3.5 will be declared as the low. Okay, that's why we never less than 4.4 lah. Okay, so unless the noise proper operation is introduced, and then the voltage on this line, okay, for this line never exceed 0.33 unless a noise or improper operation is introduced. Okay, that characteristic is the speed of operation. Okay, the speed of operation of the digital circuit is specific in terms of the propagation delay time. Okay, so the input and output waveform of the logic gate are shown in the figure here up to this. Alright, so the delay times are measured between the 50% voltage levels of the input and output waveform. I will show up to you. Alright, so we have two delay times. Okay, so we have the time delay high low. We can put as the high state. Okay, and for and then another one is the low state high state and low state. Okay, so for TP RHL, when the output goes from the high state to the lower state, and then TP LH is corresponding to the output making the transition from the low state to the high state. Right, and then the propagation delay of the logic gate is taken as the average. Okay, average of these two delay times. Okay, so you can see here. Alright, so this is a some example of the speed of operation. So this is the not ideal lah. For example, for ideal like this, okay, is alright. Oh, sorry, it's not so nice. The ideal is a straight lah. Okay, is will be like this, will be straight lah. Will be nice. Okay, will be nice. Okay, so maybe like this lah. Very nice. Okay, nice. Okay, this one will be like this. They mentioned this is ideal lah. This is ideal, but this one is not ideal lah. So that's why we measure from the 50%. Okay, 50% from low to high. Okay, that means it's the positive going past. This one negative going past. Okay, 50%. Right. So 50 and here to the output. Okay, and then here is also 50%. Okay, from the output. So this one we can guess the TPHL for the high state. Okay, and then this one is the low state. Okay, so next we go for the next characteristic. We go for the power dissipation. Okay, so this IC, this is the amount of power dissipation in the IC lah. So it is determined by the current, okay, ICC, that is the draw from the VCC supply, and is given by VCC multiplied by ICC lah. Okay, so this is a formula for this one formula for calculate the power distribution lah. Right, so how to get the ICC? Actually, ICC is the average value of the low and high. Okay, so that's why here. So this one for low, this one for high, and another one for the low. Divide by 2, you can get the average. Okay, get the average power supply. So the average power supply multiplied by VCC. So that is the average. Okay, average power dissipation. All right, so this is the power dissipation. Okay, so this is some example of the power dissipation. So you can see some example here. So we have two conditions. So when the gate is high input state, and the amount of current dissipation generated by ICC is drawn, as you can see here, on the figure A here. And for the B, so low output state, and then the amount of current generated by the LCC, L is drawn, as you can see in the figure B here. Okay, next characteristic of the IC is the figure of merit. So the figure of merit of the digital IC is defined as the product of speed and power. So this one we can call as the speed power product. Okay. So the speed is the specific in terms of the propagation delay time expressed in the nanosecond. So for example, the formula of figure of merit is the equals to propagation delay times normally in the nanosecond multiplied by power. Okay, power in the milliwatt. Okay, so in specific normally for figure of merit in the picojoules. Okay, picojoules. That means nanosecond multiplied by milliwatt equals to picojoule. Right? So the low value of the speed power product is the desirable. Okay, in the digital circuit, if it is desired to have high speed. So for example, like if low propagation delay, then there is the corresponding increase in the power dissipation and vice versa. All right. So this is for the figure of merit. So next, this is last characteristic of the find out. Find out. Okay. Okay, last characteristic of the IC lah. We call a find out. Find out is when the output logic gate is connected to one or more input of another gates. The load on the driving gate is created. Okay, so as you can see in the figure here. So this one we can declare as the driving gate, and this one is the load gate. So this is the limit. Okay, this is the limit here. Okay, on the load gate inputs, that is given gate can be drive. Okay, this unit is the called fan out of the gate. Okay, all right. For example, for CMOS logic, we have two types lah. We have the charging and discharging. So you can see here. So we have 5 volt here. So here will be flow for the next. Okay, so this one we can call the charging lah. Okay, for CMOS, will be charging, and this one is the ground. All right. So this one we can call as the discharging. Okay. For the TTL, all right. So TTL loading. All right. So this is we can call as the current sourcing. All right, from the supply. All right, from the supply. So and then from the current seeking from, okay, from this one. All right, go for this one lah. Okay, this one we can declare the current seeking, and this one is the current sourcing lah. Okay, so next on the chapter 5 is the fixed function integrated circuit lah. So this is for IC package style. So that means type of IC lah. So sometimes IC can package style lah. You can replace the plate, okay, dual line package DIP, leadless ceramic chip carrier, okay, small outline IC, and then another one is the plastic leaded chips carrier lah. So this is some package IC, the type. Okay, for example, like example. So this one, so this one, maybe you can see this one. So this one we can call as the flat packs IC lah. So the package of IC. So maybe you can see, okay, another one. So this one is normal. You can see like this one, So this one we can call as the dual inline package. Okay, so this one, okay, maybe you are familiar this one lah, inline package. Okay, so you can see we have the nodes here, and then we have the pin 1 identifier. All right, so this one is pin number 1 until pin 15 lah. So every pin they have the function. That's why you have to refer to the data sheet of this IC. Okay, but this one we can call as the dual inline package. All right, so another one, maybe you can see this IC lah. So this one we can call as the leadless ceramic chip carrier. Okay, similar like this. So they have the pin 1 identifier. All right, so this one normally you can refer to the data sheet lah, the function of every pin. Okay, and then I think this one also you have to mostly found this one, small outline IC lah. Right, so you can see in the end view. So maybe like this. Okay, so will be same. Okay, will be same. We have the pin 1 identifier. All right, and then last one we have the plastic leaded chip carrier. So this is the package of the IC lah. So only we can find the small outline, okay, small outline IC, and another one is the dual inline package lah. This normal normal IC that we use in our lab lah. Okay, so for this one maybe you can find on the small electronic component and so on. Okay, I think that's all for chapter 5. Chapter 5 that means is the more theoretical lah. More theoretical is related to IC, integrated IC. So the type of IC, okay, the characteristic of IC. Okay, what is the characteristic? You have 5 characteristics of IC. Okay, you have to know. So normally all the characteristic, the spec, okay, the IC, every IC you can find on the data sheet. So that's why the IC came with the data sheet. So for example, like on the data sheet you can know the every pin, okay, for example here. So what is the function for pin number 3, pin number 16? So every pin they have their function. For example, for pin number 3 is for VCC, and then for pin number 14 will be ground, for example. That's why when you do connection, so you have to know every pin. Okay, so this one normally we can refer to the data sheet. Alright, so every pin they have this and have the function. Okay, so that's mean that I mentioned to you. So every IC you have to connect with the VCC. Okay, okay, VCC to on this IC. That means to on this IC. Even okay, so we have total circuit here. So this total circuit already on, but if your IC is not on, so that's still not function. Okay, your circuit is still not function because this IC is also need a VCC to on this the IC, yeah, inside the IC, right? So on the IC, inside the IC we have the module. Okay, the module actually is the conventional okay logic circuit lah. For example, from this conventional will be function as the adder, for example, is the flip flop or okay for demultiplier, okay, demults and so on. Okay, and then we have three type, okay, three type of the IC. We have the CMOS, okay, we have bipolar or TTL, and another one is the by CMOS lah, okay. All right, I think that's all for the chapter 5. Chapter 5 is the theoretical, theoretical, but we have one question for the final for the chapter 5. Okay, so that's why we have to cover. We have to cover for chapter 5 for this semester. Okay, so we stop here. All right, so this is for our finish out our syllabus for digital electronics. Okay, until chapter 5. Okay, all right, so today we will discuss about the tutorial. Okay, tutorial. Right, so thank you very much. Okay, assalamualaikum warahmatullahi wabarakatuh.